Yeah, I'll record.
Okay. Okay, there. Okay, so last time we were looking at two-dimensional easing model, uh, and we said that like we look at a system which is defined on a two-dimensional square lattice with uh, ferromagnetic interaction both in x as well as y direction. But we assumed that the interaction need not be equal. So interaction in x direction is j, whereas the interaction in y direction is j prime. And we started off with anisotropic coupling, namely j not equal to j prime. Okay. And our plan was basically to obtain quantum Hamiltonian for this system and then study the corresponding partition function. Okay. So so let's start with the classical expression for the energy. Uh, so along the x direction, so suppose you pick any point r on a two-dimensional lattice, then r plus ex hat is the nearest neighbor to r in the x direction, and r plus ey hat is the nearest neighbor in y direction. And the energy functional is written in terms of minus j times the nearest neighbor spins in x direction minus j prime times nearest neighbor spins in y direction. Okay. Now, as I mentioned last time also, that we are considering the system only with the nearest neighbor couplings with no external magnetic field. Okay, so that is some thing one should note, because as we start manipulating this stuff, it would look like the different setup as we define these variables. Okay. Good. So the partition function for this system is written as Q is equal to exponential of minus beta E, where E is the energy function written up here. And as we mentioned last time, we are choosing free boundary condition in x direction, there's periodic boundary condition in y direction. And I mean, we could have chosen periodic boundary condition in both directions. In that case, you would have to add one more term to the energy functional, which allows the nth site in the x direction to interact with the first site. Okay, so that would have been one extra term in the energy functional. Okay, so the idea was to compute row-to-row transfer matrix. In other words, like we know how to compute partition function for a chain. Then we couple a chain, one chain to the nearest neighbor chain. Okay, and we construct that matrix which tells you how spins n1 along the x direction interact with another n1 spins which is in the next row in the y direction. Okay, and that would be written in terms of a transfer matrix T. This transfer matrix would have been a 2 by 2 transfer matrix if you fix a particular location in the x direction. That spin would be talking to the same x location, but y location shifted by 1 or by a unit vector in y direction. So, and that is a 2 by 2 matrix. But that 2 by 2 matrix is to be written for each of the n sites. So that effectively becomes 2 to the n1 cross 2 to the n1 matrix. Okay. There are various different ways of doing this counting, but eventually it comes down to writing down a matrix of this kind. Okay. Now, of course, we would be writing this in terms of 2 by 2 matrices, but each 2 by 2 matrix is site specific. So our next 2 by 2 the 2 by 2 matrix for the next site is different from the 2 by 2 matrix that we have written for say site R. Okay, and R plus EX hat is a different matrix. In that sense, it becomes a larger and larger matrix. Okay, fine. So, of course, when we are writing down this row-to-row transfer matrix, the coupling is of course given by J prime because that is the coupling in the. Hello, can you hear me?
No, we lost you for a minute.
Because it said the connection is bad or something. Okay, can you hear me now?
Yeah.
Yeah.
Okay. So, so since we are doing row to row transfer matrix going in y direction, our coupling is given by the y direction coupling, namely J prime. Okay. Uh, so, uh, so let's kind of look at this expression. So let's write down the matrix elements which are uh, in uh, in the x direction, which will for our first row, let's call them SM. Okay, and in the second row, which is the row next to the to which the first row is coupled to, and let's call them SM tilde. Okay, of course, m will take in one value because that is the number of sides in the x direction. Okay, now remember spin can take only two values. These are easing spins, so it can take +1 or -1 value, and we can kind of mimic that by writing a polymatrix. Okay, so instead of writing a spin degree of freedom, we could just write down polymatrix whose eigenvalues are +or -1. Okay, fine. So so let's kind of simplify our notation by not writing beta times j or beta times j prime, but let's write down k and k prime. And if we do that, then uh, along the first row, we know what to write. This is something we had done when we studied the one-dimensional Ising model or the Ising spin chain. Okay, and that is exponential k s m m plus 1 along the x direction, that is by k, which is a beta j factor, and no j prime because that's a coupling in y direction. And that gives you an expression like this, now replacing spins by polymatrices. Okay, and now we want to ask how individual spins interact with the spins in the y direction, which will of course involve coupling k prime. Okay, so for that, we of course need the interaction of SMs with SM tildes. Okay, so let's write down the row-to-row transform matrix T1, which is the interaction between these two rows of spins, and that is given by a matrix like this, where for each site M in the x direction, it is a 2 by 2 matrix. Okay, and uh, and the interaction is like this, that if both the spins are pointing in the same direction, then it is e to the k prime. Okay, but if they are pointing in opposite direction, then it is a minus k prime. Okay, so diagonally it is you get e to the k prime, out diagonally you get e to the minus k prime. Okay, so what we'll do is we'll pull out e to the k prime and write this as 1 plus e to the minus 2 k prime times sigma 1, because uh, when you pull out its k prime, then that term is proportional to identity, which is this factor, and e to the minus 2 k prime factor is proportional to the polymatrix sigma 1. Okay, uh, this polymatrix is of course a constant matrix, but it has a location level m. Okay, so this m has nothing to do with the entries of the matrix, but it is keeping track of the Hilbert space on which this sigma matrix is going to act. Okay, and that is a Hilbert space defined at the mth lattice sites. Okay, fine. So that's what is this polymatrix. Okay, now uh, polymatrices have certain properties which will be useful for the manipulations that we are going to do. First of all, they are Hermitian matrices, sigma 1, sigma 2, sigma 3, all of them are Hermitian, and they square to identity. Okay, and the third property they have, which of course contains the fact that they square to identity. In fact, this formula also contains the fact that they are Hermitian, and that is that if you take sigma A times sigma B, then that is equal to delta AB plus I times epsilon ABC sigma C. Okay, so we will need to use this property as we go ahead. Okay, so the first consequence of the fact that it squares to identity uh, is that if you write down an exponential function involving sigma, then that function is at most linear in sigma, because quadratic powers of sigma are proportional to identity, and therefore cubic powers of sigma are proportional to linear terms in sigma. Okay, so therefore you can use this fact that it squares to identity to write down an exponential function involving sigma polymatrices as a function which is independent of polymatrices plus a function which is linear in polymatrices. Okay, and one can explicitly check this result by just purely expanding this exponential and using the fact that sigma polymatrices square to identity. Okay, fine. Now remember that we had this factor is the minus 2k prime sitting here. Okay, and so what we'll do is we'll define that. We'll write that in terms of some other variable, and we say that like tan hyperbolic k tilde would be written as the exponential of minus 2k prime. Okay, so this is for convenience in the sense that like if we do this, then the expressions can be simplified. Okay, of course this relation is invertible, so one can always go back and write everything in terms of k prime if you wish. Okay. Anyway, so what happens is that like you would replace this e to the minus 2 k prime by tan hyperbolic k tilde, and so if you pull out the denominator piece, which is cos hyperbolic k tilde out, then you get a term which is cos hyperbolic k tilde plus sigma 1 m times sin hyperbolic k tilde, which is a numerator of tan hyperbolic function. Okay, and this is a place where we will use this polymatrix identity, which is cos hyperbolic plus sigma times sin hyperbolic can be written as an exponential function. Okay, so if you do that, then you actually land up with this relation for T1. Okay, so the first two terms are identical. Numerator denominator exponential k prime upon cos hyperbolic k tilde. That piece is as it is. And the last piece is written as exponential k tilde times sigma 1. Okay. So from this formula, it just corresponds to the statement that n hat, the unit vector that one is looking at, is in the x direction. That's why n hat dot sigma just gave us sigma 1. Okay. 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 So this is the expression for mth site, and we. Okay. So we of course have to do take a product of this matrix for all n's. Okay. So therefore that would give us 2 to the n1 cross 2 to the n1 matrix. Okay. Fine. So one way to write this is to kind of just write this expression. Remember, the first term is independent of m anyway, so it just goes to n1's power. So that's why you get exponential n1 times k prime and cos hyperbolic to the n1 times k tilde. The piece which depends on m is sitting in the exponent. So therefore, when you take products of all these, it just corresponds to taking sums of those terms in the exponent. Okay, so that is why you get a sum over m going from 1 to n times k tilde times sigma 1. This is the term that you get by writing down row to row transfer matrix. Whereas the last term, which is exponential k sigma 3m plus 1, was the piece which came from the transfer matrix of the Ising chain that we started off with. So let me just go back a little. Looks like the network is bad again. So this is a piece that the term in the first row that we had computed in 1D Ising model. So that piece is also part of the partition function. So we write down that term also. Okay, so that is the transfer matrix that we get by computing the row term first and then row to row term, which is this exponential times this constant factor. Okay,
Sir,
fine. Yes.
is there a reason why, like, it won't matter if the two exponential were swapped, because in the end we would be taking trace and we would get the same value. But even this could happen, right? Like the summation in like the first exponential, where we
Yeah.
have summation in sigma 1,
Yeah.
this could appear in between the second exponential, like each term.
Each term is this.
The first sigma 1, the sigma 1 corresponding to m equals 1
Yeah.
sits at the first in the left, uh, and even this the second exponential.
He's saying instead of writing sigma and sigma, you write exponential k tilde sigma 1 and then the second term and write a pi outside. So it will be ordered
Yeah,
multiplication.
it would be some kind of alternate terms coming from the first exponential and the second
Yeah,
exponential.
like in the path integral
Yeah.
also we have that only
Yeah.
px, px, px.
Yeah, that
So
is right. You could have done that, but the thing is that like sigma 1 doesn't commute with sigma 3, no?
yeah, that's why I'm asking. Like, is
That's why they
Yeah.
are inequivalent, he's saying.
yeah. So is there a reason why we are writing it like this?
Well, I mean, what we are doing is basically we are computing a partition function for a chain and then interaction of chain with chain, right? That is why we get expressions like this. Okay.
Yeah,
Eventually,
actually,
what we are going to do is to actually get them together, right?
yeah, but I don't see why like we can independently calculate the terms due to interaction between two rows and the interaction of single row, and we can simply take a product of these two exponentials.
I think
It
that
could have
can
been
be
more
No,
done
complicated, right?
when k and k tilde are small.
no. See, each term, uh, see, this is a term at mth site, right?
Yes.
And this is a term at mth site along the x direction, and that was along the y direction, right? So the exponential is there all the time. So total t that you would write down at mth site is the exponential of product of this exponential with that exponential.
Yeah,
Right?
so we should maintain the order, right? Like at m equal 1, we are writing exponential k tilde sigma 1 at 1 into exponential k sigma 3 at 1, sigma 3 at 2.
Yes. Oh yeah,
Then
yeah. Okay,
then
if
the
that is what is
second
worrying you.
matrix.
Yeah. If that is what is worrying you, then first we will see as we go ahead that sigma matrices at mth site commute with sigma matrices at nth site if m is not equal to n. Okay,
Yeah.
they're totally independent. So you can take this product and kind of rearrange any which way you want. Okay, as long as the site exponential at site m and another exponential at site m, they are not swapped. You know what I'm saying?
Yeah, but still the next term would have been sigma 1 m plus 1. Like,
Yes, yeah,
and that will not commute with sigma 3 m plus 1.
that is right. Yeah, that is right. So,
So
so
then
there
we
is
cannot write it this way.
a yeah. So what we are going to do is not that. What we are going to do is use the path integral technique to say that if one of the quantities is small, these two exponents can be written as a single exponent with some of these two quantities.
Yeah, then it might be possible.
Yeah. So if you just go ahead, we'll see what happens. We'll have to take a high asymmetric limit, but we'll get it. This is exactly the way we kind of separated the exponential of e to the p squared by 2m and v of x.
Yeah.
Right. We are going to do the same thing only in the reverse order. There we had a single exponent and we separated that into two exponentials. Here we have two exponentials and we are going to combine them into single. Okay. Let's go ahead and we'll see what is happening. Okay. So the total partition function would be, of course, taking n to th power of this row to row transform matrix, because it is already taking everybody in the x direction. but only 2 fellows in the y direction. We have to take n2 of them because there are n2 such sites along y direction. Okay, so that is what would be the total partition function. This trace is a statement that in y direction we are taking periodic boundary condition. Okay, so of course, to do this, it would be best if we could kind of diagonalize the transfer matrix. That means determine its eigenstates and eigenvalues. Then, of course, a diagonal matrix would be easy to kind of take its product and take trace. So let's kind of denote the eigenstate by alpha, and let the eigenvalue be T alpha for the state alpha. Okay. Now, remember, we have to take thermodynamic limit. That means n1 times n2 going to infinity. We would really want to do n1 going to infinity, n2 going to infinity kind of limit. Okay. So in that case, what happens is that like the largest eigenvalue of the transform matrix is the most dominant one. Okay. Any eigenvalue which is kind of lower than that eigenvalue is exponentially suppressed. Okay. So therefore, what we are interested in really in this particular case is to look for the what we would call the ground state of the system, which would be the largest, which would be the contribution coming from the largest eigenvalue of the transfer matrix. Okay, fine. So now, of course, remember this as we were just discussing that one piece contains sigma 1, the other piece contains sigma products of sigma 3. So we could individually diagonalize these fellows. Remember, we had done this diagonalization in the using chain case. Sigma 1 diagonalization is just corresponds to doing a similarity transformation, which replaces sigma 1 by sigma 3, which brings it into a diagonal form. But the matrix which would diagonalize this wouldn't diagonalize this. Okay, so therefore, in spite of being able to individually diagonalize the term, since the two terms themselves do not commute with each other, we cannot diagonalize the full transfer matrix. So what we will do is basically combine two exponentials into a single exponential, and then try to diagonalize that exponential. Okay, and then again we will need the Baker-Campbell-Hausdorff formula, which is written out here. Okay, and of course, in the original, if you have done path integral in quantum mechanics, then we have used this same Baker-Campbell-Hausdorff formula, but in the reverse order. We wrote e to the epsilon a plus epsilon b is equal to is the epsilon a times e to the epsilon b minus not minus times exponential of minus epsilon squared by 2 times commutator of AB and so on. Of course, there are infinite number of terms, at least the number of terms until the commutator vanishes. Okay, so and if it never vanishes, then there are infinite number of terms. Okay, so as we did it in path integral, this separation where you can ignore this commutator piece would happen only in the limit when you are taking epsilon into 0. Okay, so in the case of path integral, it has a nice interpretation by saying that you take the steps, the time steps to be very, very small, very refined time steps, and if you do that, then for arbitrarily small time steps, the commutator term is suppressed compared to the other two terms which are linear in epsilon. Okay. In this case, of course, you don't have explanation like that because epsilon going to 0 corresponds to. Okay, so I need to show what the epsilon is. So in this particular case, we have these factors sitting around. One of them has a k tilde, other has a k, and epsilon going to 0 limit actually corresponds to taking k and k tilde to 0. Okay. Now, taking k and k tilde to 0 does not mean that you are taking both the couplings to 0, because k tilde was a tan hyperbolic of k tilde was related to k prime, which was the coupling, which was related to coupling in y direction. So k tilde going to 0 actually corresponds to k prime going to infinity. So it's kind of an asymmetric limit in which x direction coupling is small and y direction coupling is large. Okay. Now, of course, you don't have to take it to infinity or something, but nevertheless, it's a asymmetric limit. Okay, it's kind of extreme anisotropic limit. But if you take that limit, then in that limit, you can actually combine the two exponential and write down the Hamiltonian as sum of those two terms. Okay, so now you don't have an exponential of k tilde times sigma 1 times exponential of k times sigma 3, but you have just single exponential which contains both these pieces. Okay, it's exactly same process. The path integral must run in the opposite direction. Okay, now if you do that, then you can ask a question, how do you diagonalize this piece? Okay, now the interesting thing here is the following, that remember, if you when we started off with this model, we said that this model has a nearest neighbor coupling in x direction given by j and nearest neighbor coupling in y direction given by j prime, and we said that we are not using any external magnetic field. Okay, at the end of the computation, what we get is a Hamiltonian which has a nearest neighbor coupling. Okay, sigma 3 is the representation of spin, so it's a nearest neighbor coupling there, but on a chain, and that chain is only in the x direction. Okay, and on that chain you have a magnetic field. Okay, so what we have done is we have reduced the two-dimensional Ising model, classical two-dimensional Ising model problem, to a one-dimensional quantum Ising chain. Okay, but not only that, it is a one-dimensional quantum Ising chain, it is a chain in the external magnetic field, and the external magnetic field is given by k tilde, but that is not in the z direction, but it is in the x direction. Okay, so this is a model which is the Ising spin chain in what is called a transverse magnetic field. Okay, so we have reduced the two-dimensional problem to a one-dimensional problem in the presence of magnetic field which is transverse to the values that Ising spin would take, which are parameterized by sigma 3. Okay, is that fine?
Would you go to previous slide?
Go to previous slide.
Yeah, this the above one. Yeah, exactly. Is this exactly solvable, the Hamiltonian, like for arbitrary k and k tilde?
Yes. In fact, we'll do the map now.
Okay.
Okay. So we will map it to a new system, and that is done by what is called the Jordan-Wigner transformation. Okay. So what we want to do is to actually solve this problem. So find out the eigenvalues for this Hamiltonian. So there are multiple ways of doing it. Jordan-Wigner is just one method. Okay. But let's follow Jordan-Wigner because this is a little different from what we have done earlier, in which we did everything using only transfer matrix. That is how the 1D Ising model was solved. 2D Ising model also can be solved by completely following the transfer matrix technique and pushing it all the way through to get diagonalizing the matrix and finding out the eigenvalues. I'm not doing that because that is some technique that you could kind of learn by just generalizing whatever you have learned for 1D Ising model. This is a new technique. In the process, you'll end up learning too. Okay, fine. Okay, so this is a very elegant technique and it is useful in many places actually. But let's kind of apply it here, and if you kind of look around, you will find that Jordan-Wigner is used at like in number of places really. Okay, so what is the idea? Idea is the following, that you have this Pauli matrices written in the Hamiltonian, sigma 3 and sigma 1. And what you do is that you replace that by a fermionic variable. Okay, so you define a fermionic operator in the following way. Okay, so you call the operator psi2. Okay, so you call the operator psi2 defined at a site M because there is a sigma 2 sitting there at that site M. Okay, and that sigma 2 is multiplied by sigma 1 from the left from site 1 to m minus 1. Okay, so you can imagine that like you have a chain of sigma 1s, and the place where the fermionic operator is sitting, site 2, that is the place where sigma 2 is sitting. Okay, so clearly this is kind of a non-local operator with respect to Pauli matrices. Okay, but that defines the fermion at location m. Okay, we define another fermion psi 3 at location m, where instead of sigma 2 you have a sigma 3. Okay, and this sigma 3 is also preceded by a chain of m minus 1 sigma 1 matrices. Okay, so we define two fermionic operators, psi 2 and psi 3 at site m. M of course can take any value, 1, 2, all the way up to up to n1. Okay, so that many fermionic operators are defined, 2 at each lattice site. Okay, these fermionic operators are called Majorana fermions. Okay, fine. So this is something I had not defined as a representation when we studied Lorentz group, but Majorana fermion is basically like the Dirac fermion, except that it satisfies a reality condition. Dirac fermion is complex fermion, whereas Majorana is a real fermion. Okay, so clearly, therefore, Majorana fermion has half the number of degrees of freedom compared to the Dirac fermion, because Dirac fermion has in 4 dimensions, of course. In 4 dimension, Dirac fermion has 4 components, and each component is complex. That means it has actually 8 real components. But then there is an equation of motion which reduces them to 4 real. Okay. Whereas Majorana fermion also has 4 components like Dirac spinor, but they are real. So therefore, it has only 4 real components. But then the equation of motion reduces them to only 2 real components. Okay. So in that sense, you can construct Majorana fermion by writing a real Dirac fermion. Okay, fine. So reality condition is like this, that you say that psi alpha dagger is equal to psi alpha. Okay, so that corresponds to the statement that you take a dagger on this at any site, say mth site. If you take dagger, this operator has to go back to itself. Okay, but that's kind of trivially true, because all sigma matrices are Hermitian, but when you take a dagger, then they are in opposite order. Okay, because a times b whole dagger is b dagger a dagger. Okay, so therefore all these operators will kind of appear as sigma 2, sigma 2 at m, sigma 1 at m minus 1, sigma 1 at m minus 2, up to sigma 1 at 1 at the right extreme place. But since they act on different Hilbert spaces, they commute with each other, and therefore you can rearrange them back into this form. Okay. So therefore you can easily check that psi 2 and psi 3 are both Hermitian operators. Okay. Next condition that the Majorana fermion satisfies, that is squares to 1. Excuse me. Okay, so that the square to 1 is also quite easy. You just kind of juxtapose this operator with itself, and then you will find that if you write down psi 2m, then these operators kind of just multiply each other. But since these fellows act on different Hilbert spaces, they just cut across and sit next to each other, and then sigma 1 n square is equal to identity. Okay, for any n, and similarly sigma 2 m square is also identity, and therefore this entire product squares to 1. Okay, and this is true for both psi 2 and psi 3. Okay, fine. So it's a bit of a weird notation to not write psi 1 psi 2 but write psi 2 psi 3, but it has reason, because if you write psi 1 psi 2 and write down sigma 1 sigma 2 to be psi 1 and sigma 1 sigma 3 to be psi 2, that could be potentially more confusing than this, but at least that's what I think. Many books also follow this kind of notation. Instead of writing 1 and 2 here, they write 2 and 3. Okay. Okay, so this is the same thing that I told you, that the sigma matrices commute if they are defined at different lattice sites. Okay, so as a result, just a second. Yeah, as a result, the polymatrix commutation relation needs to be kind of rewritten a little more carefully in this particular case, because earlier what we used to write was the polymatrix commutation relation uh, for polymatrix defined at no specific lattice site. But now we have polymatrices acting on specific Hilbert spaces defined at a specific lattice site. So therefore, the commutation relation gets modified to sigma A at site M, commutator with sigma B at site N, and this commutator is non-zero only if M is equal to N. That is this delta Mn, which is enforcing that this is a non-trivial commutator only if M is equal to N, otherwise they just commute. Okay. So if M is not equal to N, this entire stuff is zero because delta Mn would vanish. Okay, and if M is equal to N, then of course this delta Mn clicks to be 1, and then you get the usual commutation relation. Okay, so that is the commutation relation that we will use, and that is the reason why we are allowed to move all these sigma n's. When you take the dagger of this thing with oppositely ordered expression, you can just push it through and bring it back to the same form. Okay, so what we have done is that we have replaced sigma uh, string of sigma 1s ending with sigma 2 or ending with sigma 3 in terms of these fermionic operators. Okay. Now notice that like we actually encountered sigma 3 matrices and sigma 1, but we didn't encounter sigma 2 matrix at all. Okay. So we need to understand as to what is the utility of this when when it comes to writing down the Hamiltonian of the system. Okay. So yeah. So let's try to first consider the anti-commutation relation of these Majorana fermion operators. Okay, so that is this expression psi alpha m, psi beta n, where m is of course not equal to n. Okay, now notice that if why are we looking at this? Because if m was equal to n, then we know that psi squares 2 identity, right? That is one of the properties of the Majorana fermion. Okay, so therefore we don't even need to look at same site anti-commutation relation. So we need to look at the anti-commutation relation when the fermions are at different sites. Okay, fine. So there is nothing lost in assuming that m is less than n. It's a symmetric product. Anti-commutator is symmetric product, so it doesn't matter how you write it. Okay, so let's see how this expression is going to look like. So, okay, maybe I split the screen. Yeah. Okay. Fine. So now suppose you are looking at this product. Okay. You are looking at psi alpha at m with m less than n and psi beta at n. Okay. Then you have sigma 1 going from n is equal to 1 to m minus 1. Okay. That piece, which whether it is whether alpha is psi 2 or psi 3 doesn't matter. Okay. But there is a string of sigma 1s all the way up to site m minus 1. That string will be repeated in psi beta also because n is larger than m. Okay, so but every time sigma 1 squares, it is just identity, and therefore that entire piece will drop out. So the first non-trivial polymatrix that you would have in this series is the sigma alpha, whatever is alpha value, at site m. So either it is sigma 2 or sigma 3. Okay, then psi beta at n would also have a sigma 1 matrix at site m, but because psi beta is on the right, this sigma 1 is on the right of this operator. Okay, and then that series continues all the way up to n minus 1, and then there's a sigma beta, whatever is the beta value, 2 or 3. Okay, so this is the piece that we would land up with. Okay, so this is what I explained, that for any L less than M, that piece would trivially cancel. Okay, we want to compute anti-commutators, so we should arrange them in the opposite order also. So if we arrange them in opposite order, remember n is greater than m still. Okay, so if you arrange them in opposite order, then this fellow has sigma 1 going from n is equal to 1 to m minus 1. Okay, actually up to n minus 1, but up to m minus 1, which will cancel with sigma 1 of this fellow up to m minus 1. Okay, then you have a sigma alpha coming from this psi alpha, but that has to be on the right because of this product, the order of this product, and sigma 1 m is on the left. Okay, contrast that with this, where sigma alpha is on the left and sigma 1 is on the right. Here you get it in the opposite order. Okay, so you have that, and then of course this fellow has sigma 1s going all the way up to n minus 1. So those pieces are sitting around, and then a sigma matrix corresponding to psi beta. Okay, fine. So okay, good. So now when you write down psi alpha plus psi beta piece, okay, then let me kind of remove this for the time being and see if I can keep both of them together. Okay, so we want to add these two pieces. Okay, when you want to add these two pieces, you will notice that sigma 1 m plus 1 all the way up to sigma beta n, this entire piece is common to both of them. So you can, and everything is on the right, so you can keep it there, and the two pieces on the left are the anti-commutator of sigma alpha with sigma 1. Okay, that is the piece that you get. Is that okay? But the anti-commutator of sigma alpha with sigma 1 is just 0. Why? Because alpha is not sigma 1. Okay, alpha is not 1. Alpha is only 2 or 3. Okay, and if it is 2 or 3, then the anti-commutator is sigma 1. That is the property that polymatrices have, and therefore this anti-commutator just vanishes when m is not equal to n. Okay, is that fine? Okay, so now we can use these operators to write down the Hamiltonian in terms of these fermionic operators. Okay, so let us start with so let us start with this expression. Okay, or maybe I should. No, it's okay. Okay, so let's suppose you start with psi 2m, psi 3m. Okay, psi 2m and psi 3m are sitting at the same site. So therefore, this entire string of sigma 1s, okay, that you would have had going from n is equal to 1 to m minus 1 will just cancel out, because all of them have sigma 1s at site 1 square, sigma 1 at site 2 squared, and so on, all the way up to m minus 1 site. They all go. Then you get a sigma 2 matrix, and then you get a sigma 3 matrix. But sigma 2 at site m times sigma 3 at site m is just I times sigma 1. Okay, so you get a sigma 1 matrix by taking a product of this kind. Okay, for every m, you get a sigma 1 matrix exactly at that site m. Okay, so what we will do is that we will write down sigma 1 m, okay, as minus I times psi 2 m psi 3 m. Okay, remember this was one of the terms in our Hamiltonian. Okay, so let me take you back to this chain Hamiltonian. Okay, this is a term that we have, sigma 1 m, which is to be summed over all m values, but that can be written in terms of fermion bilinear now. Psi 2 m times psi 3 m, okay, with some minus I factor sitting around. Okay, good. Now let's consider the next one. So let's go down again to the see. Now let's consider psi 2m times psi 3m plus 1. Okay. Now, if you look at these pieces, then again up to m minus 1 sigma 1 pieces would just cancel out. Okay. So what you have is sigma 2 at m. Then you have a sigma 1 at m because psi 3 would have a sigma 1 at mth location. Okay. And then you have a sigma 3 at m plus 1. Okay. So that is all that survives. Everything else gets killed. Okay. Is that fine? We had done this same calculation earlier. Okay. Here. That when you take this, only m to n terms survive. If n is m plus 1, then you have only three terms sitting around there. Okay. Is that fine? But now out of these three terms, two of them are sitting at the same site. Okay. And they are in this order, sigma 2m times sigma 1m. But sigma 2 times sigma 1 is actually minus I times sigma 3. Okay. Fine. So therefore, what you get is that sigma 3m times sigma 3m plus 1 can be written as I times psi 2 at m times psi 3 at m plus 1. Okay. And that was the second term that or rather first term in our Hamiltonian. Sigma 3m times sigma 3m plus 1. Okay. So what we have done is that we have replaced this by fermion bilinear, and we have replaced this also by fermion bilinear. Is that okay? So eventually, this entire Hamiltonian can now be written in terms of fermion bilinears. Okay. That's fine. Okay, so here's the form of the Hamiltonian. After you do all these transformations, okay, and so I have also kept the factors of i's which were there in this transformation, which makes it minus I k times psi 2 psi 3 at m plus 1 and plus I k tilde times psi 2 psi 3 at m. Okay, fine. So okay, so now one other thing that we could do, since everything is fermion bilinear, is that you could kind of redefine the quantities, you know, psi 2s and psi 3s, and soak up the factors of k and write down k tilde by k and call it lambda. Okay. If you don't like that, what you could do is that you can just pull out a factor of k and then you get k tilde upon k factor, which you can call lambda. Okay, any which way. If you don't want to kind of manipulate fermionic operators, you can just pull the overall factor outside. Okay, that overall factor is not going to play any important role because it is these two terms involving fermions which are more important and their coupling. Okay, so what we have done is basically traded off two parameters, two single parameters, and an overall factor sitting around. Okay. Sorry. Okay, so now if you take n1 going to infinity limit, then you would kind of recover some kind of translation invariance, because you could write down this term as a term which is defined at the same lattice site plus a derivative of one of the fermions. Okay, so you kind of recover the kinetic term involving the derivative in the chain direction. Okay, so in some sense you recover the translation invariance of the system. Okay, and to see that thing, the best way to do that is to do the Fourier transform and write down the momentum space operators, fermionic operators, by writing down psi alpha m as integral over k times e to the I k m times c alpha k, where k is momentum. Okay. Now, what we will do is that, like, although this is kind of an integral done on the fundamental domain or the Brillouin zone or something, because of the reality condition, we can restrict this integral only for positive pi's. Okay. In other words, psi alpha dagger is equal to psi alpha is equivalent when you do a kind of complex conjugation on this one. It will tell you that ck alpha dagger is equal to c minus k. Okay, because if you take a dagger of this, you get e to the minus I k m times c k alpha dagger. Okay, so you get this expression. Any which way you can write c minus k dagger is equal to ck, or ck dagger is equal to c minus k, doesn't matter. Okay, so because of this, what you could do is that you could write down this expression in terms of c alpha and c alpha dagger and restrict this integral from 0 to pi. Okay, which is what we'll do later. Okay, or right here. Okay, so all we have done is that we have traded off the half of the Brillouin zone to positive k values by writing down c alpha and c alpha dagger. The advantage of doing this is that in this kind of form, reality condition on Majorana fermion is absolutely manifest. Okay, or your left hand side is real, and right hand side is also essentially made real by just doing. If you take the Hermitian conjugation, the expression goes back into itself. Okay, does that make sense?
Why have we done this Fourier sort of transpose?
Oh, because we want to write this in terms of Fourier modes actually. Okay.
The
So
Hamiltonian itself.
Hamiltonian in the momentum space, yeah.
Okay.
It's kind of easier to manipulate. Okay. Because you see, this Hamiltonian had one fellow defined at m, other was at m plus 1, right? But in the Fourier case, they would all be defined with the same k value with some e to the I k factor, which you can easily manipulate. Okay. It's exactly the way we do it in quantum field theory also, that you have del mu phi, but it is much better to kind of work in a Fourier space which converts del mu phi to be just k squared, and then the whole thing becomes algebraic. Okay.
Are we also replacing that sum with an integral, the n1 sum? In the Hamiltonian,
no,
m equal 1 to n.
No. This sum, no.
Yeah.
We will not replace that by integral. Okay, we will keep that, and then we'll do the Fourier transform complete. Okay. Yeah. So if you go ahead, we'll see that there is a discrete delta function condition that we need to use to when we kind of implement that summation. Okay. Okay, so maybe when we go ahead, you can see that actually. Okay. Okay, so what we will do is we'll take this expression for the Majorana fermion with some momentum space representation, and substitute that into the anti-commutation relation that psi was satisfying. Okay, and carry out, of course, the k integration. And if you do that, you'll land up with the corresponding anti-commutation relation for the Fourier modes. Okay, and this is the anti-commutation relation. So it's a straightforward check. All you have to do is to kind of take that expression and plug it into the anti-commutator. You have two integrals to be done, one for the psi alpha m, the other one is for psi beta n, and you can carry out that integral. You get a delta function pieces that you need to kind of kind of use carefully to get this anti-computational relation. Okay. Fine. So you may not have done the fermionic story in the quantum field theory, but it will turn out to be something very similar. In when you do Dirac fields, then you don't use C and C dagger, but you call them B's and D's, and B daggers and D daggers, and they satisfy anti-computational relation, which is pretty much like this. Okay, it's just that this delta function is in higher dimension because you are typically doing your quantum field theory in 4 dimensions. Okay, whereas this one is being done only in 1 dimension because our problem is essentially reduced to the spin chain in quantum spin chain in 1 dimension. Okay. Fine. So what we'll do is, yeah, please.
Yeah, it seems like although we were working with Majorana fermions and spatial dimensions, but after we have done Fourier transform, this behaves as Dirac fermions.
No. Why the Dirac fermion?
Just looking at the anti-commutation relations, C alpha dagger C alpha is not equal to C alpha.
C alpha dagger.
It's
No,
not equal to C alpha. Right?
No, C alpha dagger is not same as C alpha. C alpha
Yeah.
dagger K is equal to C alpha minus K. Right?
Yeah, so that's why I'm saying.
Yeah. So what we have done is, yeah, good point. So what we have done is that we use this fact to restrict our integration from minus pi to pi to 0 to pi. Now we have liberated C alpha dagger from C alpha. Okay? Because here, like, C alpha with positive K is related to C alpha dagger with negative K, right? But here all K's are positive. So C alpha dagger with positive K has no relative sitting around here, because C alpha dagger with positive K is related to C alpha with negative K, but negative K is not summed over, right?
Yeah.
So you could have written this entire expression as e to the I k m C alpha K e to the minus I k m C alpha minus K. Okay, and not use dagger at all. Okay, but that is equivalent. Okay. So because of this restriction, this fellow has no relative written in terms of C alpha. Okay.
Okay.
So it deceptively looks like the anti-computational relation that the Dirac operators, Dirac field operators would satisfy, but that's not what exactly what they are doing actually. Okay, because in the Dirac case, you would have expressions like this, but K and K prime are freely defined from minus infinity to plus infinity, whereas these guys are not. These are defined from 0 to say infinity. We are defining only in the first Billah zone, but if you had not worried about lattice and if you had taken continuum, you would have integrated from 0 to infinity. Okay.
Yeah.
Okay. So now let's try to write down the Hamiltonian in these terms, in terms of these Fourier modes. Okay. So here it is. So we will kind of do it step by step. So let's look at the first term, which was minus I times. So maybe this was a term, but like, let me write down that Hamiltonian. I've written it down somewhere. Yeah, here's a piece. So we are looking at the first term. Forget about K, minus I times the sum. Okay, that's what we are looking at. Okay. Now, as I said, that each psi will be written as a Fourier mode expansion, 0 to pi, dk1, dk2 for psi 2 and psi 3. The sum over m is already there. Okay. And then this will give you C2 K1 and this will give you C3 K2. And C2 will come with e to the I K1 m, and C3 will come with e to the I K1 K2 times m plus 1. Okay, that is the expression. But then psi2 also has the second term, right? C2 and the C2 dagger. This has a C3 and C3 dagger. So it effectively gives us 4 terms. Okay, C2 has 2 terms, either with C3 or with C3 dagger. A term with C3 dagger has a minus sign sitting around here, and K2 times m plus 1. C2 dagger would have a minus sign sitting in the first term. So instead of writing I write down minus I and a flip sign here. Okay, and then you have terms involving both daggers, and that is a term like this. Okay, which is kind of complex conjugate of that term. Okay, so this is the full expression that you would get when you write down that in the fermionic modes in the momentum space. Okay, fine. Now, when you look at this expression, then you will find that you have to do this integration over K1 and K2, but you also have to do a sum over M. Okay, so now when you do a sum over M, then you have an expression which is e to the I K1 plus K2 times M. Okay, so if you write down e to the I K1 plus K2 times M and sum over M, then that tells you that that expression is non-zero only when K1 plus K2 is equal to 0. Okay, so this is kind of a discrete delta function condition. Okay, which looks something like this. Okay, now as a result of this, the first and the fourth term, okay, which has K1 plus K2 times M, or minus I times K1 plus K2 times M. Okay, these terms would vanish simply because K1 plus K2 equals 0. Okay, with both K1 and K2 positive wouldn't work. Okay, so of course you could say that both K1 and K2 are 0, but these are the 0 modes of this particular solution. Okay, and we can kind of ignore it because they wouldn't contribute any energy. Okay, and in fact one can show that the anti-computational relation would actually give a vanishing answer for that, but leave that aside because okay, maybe I can just do that. Suppose you remember this C2 and C3 daggers are the fellows which are just C2 and C3 with minus K values, right? Remember just a few minutes ago we were arguing about this, right? That what happens to the, well, why doesn't it look like a Dirac type operator? And the reason was there are only positive K values. But if you remove daggers, then it would be C2, C3 with minus K1, minus K2. Okay. Now, of course, our integration is not on negative values of Ks, and therefore you would rather use dagger variable. But when K1 and K2 both are 0, then whether you write them as daggers or non-daggers, it doesn't matter. And you can show that these expressions would actually eventually cancel out. Okay. So endpoint of this is manipulation is that this delta function condition tells you the first and the fourth term would just vanish, and the second term and third term would be the ones which are non-zero. Okay, so here are those 2 terms which I'm writing down explicitly. Okay, but notice that they are ordered a little different way. One is a C2K times C3K dagger, and the other one is C2K dagger times C3K. So in some sense, they are complex conjugates of each other. Okay, but that is not very surprising simply because this entire product has to be real because both of them are real fermions. So therefore, reality condition is showing up here. Okay, but that's not our worry. Our worry is that we would rather like to write our Hamiltonian in a form in which exactly the way harmonic oscillator in quantum mechanics is written, that you would rather like to write the operator in a form in which annihilation operator is to the right of the creation operator. Okay, so we will have to kind of manipulate this and write this as C2 times C3 dagger times C2. Okay, and this one is of course in the correct order, so there is nothing to worry about. Okay, but notice that C2 and C3 were the operators corresponding to polymetric sigma 2 and sigma 3, and as a result, you could just take them across. Okay, but flip sign because they are fermionic operators. Okay, so what we land up with is an expression where C2 dagger C3, which is this term, which I'm writing first now, because this term after flipping, because of the fermionic nature, would have opposite sign, and that is this expression. Okay, so the first term of the Hamiltonian is written in this particular form. Okay, minus I times integral over dk c2 dagger c3 times e to the ik minus c3 dagger c2 times e to the minus ik. Okay, is that fine? So you can do a similar manipulation for the other term. Okay, psi2m times psi3m. Okay, now notice one thing, that this manipulation, the second manipulation, is simpler than this one. And the reason is the following, that in this particular case, you had to write down C2 K1 C3 K2 with e to the I K1 M, but e to the I K2 M plus 1, because one of them is defined at M, the other is defined at M plus 1. Okay, whereas this second operator, which is psi2m, psi3m, they are both defined at the same site, and therefore you don't even get this factor. As a result, when you complete the manipulation, okay, in case of first term, you end up with e to the ik and e to the minus ik pieces, okay, because of this shift between these two operators. And that shift basically tells you that there is a derivative acting on one of the operators. That is why you get this finite shift piece. Okay. But in case of psi2m, psi3m, you don't even need to do that, because this, yeah.
If you could go back to the previous slide,
Yeah.
where you're sort of calculating that dk1, dk2 stuff.
This one?
Yeah. So the first and last term cancel out because the delta function has no point where it will contribute. Exactly. The second and third terms will give a delta k1, k2. Like
K1 minus
equals
K2. K1 equals K2, yes.
Yeah. I have a sort of a problem when you're approximating the summation over m e to the iota k1m as a delta of k1 instead of delta, like the chronicle delta.
This one.
If this sum is from m equal 1 to n1, then this value is 2 pi n1 delta k0, like the chronicle delta, not the Dirac delta.
No. Momentum is continuous.
Yeah, momentum is still continuous, but it's still chronicle delta, because for any k not equal 0, this trivially gives 0 when summed over.
Yeah.
But for k equal 0, it will give n1, like exponential is just 1, and the summation is from m equal 1 to n1, right?
Yeah. Oh,
so
you're worried about this sum being finite.
Yeah, it's finite, so that for finite sums we get a chronicle delta. Although we have the thermodynamic limit, so we can perhaps say something like this.
Yeah. So maybe I should be a little more careful. I should probably write down a chronicle delta there, and then say that, like, in the thermodynamic limit it becomes Dirac delta.
Yeah, either that, or maybe in the Fourier transform only you can perhaps take a discrete Fourier transform instead of having a continuous variable k.
Yeah, I could have done that also. I agree that this sum is translated into a sum over k1 and k2.
Sigma k1, sigma k2 sort of a thing.
Yeah. Absolutely. I could have done that. Yeah. So I kind of had in mind that I am going to take the thermodynamic limit, but yeah, maybe I can correct this. I would just write down a sum there, because that is safer, because I should be able to do it for any n1.
Yeah.
Yeah. Okay. I'll correct that then. But eventually what happens is that, like, it basically tells you that k1 is equal to k2 for the non-vanishing terms. Okay?
Yeah.
And that's why it gives you this answer. So even if it was a chronicle delta, it would have given the same answer actually.
Yeah, that I agree.
Yeah. Just a second. Yeah. Okay. So let's kind of combine these two factors together. This is the second term, which is psi2m, psi3m, and the first one was the term which was like this, with e to the I k and e to the minus I k pieces sitting around. So if you write them together, then you can write the Hamiltonian in this particular form. Okay. So all you have to do is to kind of combine. There is no C2 dagger C2 term. That's why this term is 0. Then you have a C2 dagger C3 term, okay, which comes from this fellow, which has, okay, yeah, maybe I should have shown this one. Okay, so which has a I lambda piece sitting around, okay, C2 dagger C3, okay, has a I lambda piece sitting around, and this other piece C2 dagger C3 gives you I times e to the ik. Okay, so yeah, okay, I got a sign wrong.
Yeah, it enters the Hamiltonian with a negative sign. So
it enters in the negative sign. Yeah. Okay, there's a minus sign here. Thanks. Okay, so so you can check this thing, and then similarly C3 dagger C3 would be 0, and the other piece is C3 dagger C2, and you can check that you get the expressions like that. You get a minus I times lambda here, and the other piece is C3 dagger C2 coming from here, which sits there. Okay, so what we need to do is to find out the eigenvalues of this Hamiltonian now. Okay, and once we obtain the eigenvalues of this Hamiltonian, we are kind of almost done. Basically, we have figured out how to solve this problem in some sense. Okay, good. So of course, this is the 2 by 2 matrix that we want to diagonalize. Okay, and you can find out the eigenvalues. Okay, so it's not a very difficult thing to do. Okay, and it takes a form like that. Okay, so now notice that these eigenvalues have a specific behavior. Notice that if lambda is say if lambda is equal to 1, okay, then in that case, how the way the system would behave is different from the way this eigenvalues would behave when lambda is greater than 1. Okay, so I have kind of plotted this, and unfortunately I could not save that from Mathematica. This thing, so I have taken a screenshot. So therefore, the quality of the image is not good. But I will figure out how to. I mean, earlier I could take it, but today somehow it refused to cooperate. So, so I just took a screenshot and attached it here. But I'll probably put a better quality image. So the point is that like when lambda is greater than 1, okay, in that case you can show that this spectrum has a gap when k is equal to 0. Okay, so in that case, suppose k is equal to 0, then you have this term vanishing. This term gives you 1. But if lambda is greater than 1, then 1 minus lambda is some positive piece. Okay, plus minus sign tells you that there is a symmetric gap around 0. Okay, and that's how it would look like, and the spectrum kind of grows like that. Okay, I have not plotted k all the way up to pi. One could have, but like it just monotonically grows or goes down. So nothing very great to see after a point. Okay, what is important is that it has a symmetric gap out here. Okay, fine. On the other hand, if you take lambda is equal to 1, then at k equals 0, not only sin squared k vanishes, but cos k is also 1. And if lambda is equal to 1, then this also vanishes. Okay, and in that case, you don't have any gap, and you have a kind of gapless spectrum. Okay, so it would look something like this. Okay, in fact, these plots are precisely those functions, so it's not like imaginative drawing, but it's exactly the functions being plotted. Okay, so what we'll do in the next class is basically analyze this system using this spectrum. Okay, so this is just a graphical depiction of this thing. So depending upon values of lambda, either you have a gap or you don't have a gap. And we will kind of try to show that this behavior is related to the critical behavior of the system. Okay. So I think I'll stop here today.
Here we have a sort of decay integral, right? In H.
Yeah. Yeah, like that.
So we are sort of diagonalizing at each k value and still
Yes.
integrating.
Yes. So it's not like you are diagonalizing for each k value. You are diagonalizing it for arbitrary k value, and then you integrate over all possible k. Right. So in fact, how the spectrum is exactly going to behave. So it's completely predictable.
Yeah.
Okay. Any other question?
So how will the corresponding states look like for a given eigenvalue? Like we are diagonalizing and C2 and C3 basis. I don't know.
Yes. Yeah. So you get a linear combinations of C2 and C3.
So I mean, what does it? Oh, we are creating some kind of a particle using the linear combination of C2 and
Yes.
C3.
Exactly.
Okay.
Yeah.
Okay. And that happens at each case.
Yeah, it happens at each k. Exactly.
Okay.
Any other question? Okay. If not, then can I stop the session today?